Okay, so welcome to our webinar concerning image processing and the performance considerations. I'm Björn Rude, Field Application Engineer and Product Manager at Basler within machine vision since 2002, and since 2008 having a very strong focus on FPGA preprocessing within Frangabers, and since more than 10 years at the Basler AG. So when I will explain to you what kind of image processing solution we are showing, first I will go through some basics. Then in the next step, I will explain some backgrounds, and at the end, I will go through some use cases where I can show the benefits of what I would like to explain. First of all, we have one poll in the background. I hope it's working because I somehow lost the connection to my colleagues. Just give me a second. Okay. I guess you can see the poll open. So just make your decision. So we are right now waiting for my colleague ending the poll concerning the first question.
Hello? Hello, Björn, can you hear me?
Yes, I can hear you.
Okay, yes. So, yeah, sorry for the inconvenience. So just now my connection dropped. Okay, so thank you everyone for participating in our first poll. So the question here again to recap is how are you handling image processing for pre-processing your current application? So as you can see in the poll results, the most highly voted choice here is done by using on CPUs by using common software in the market. So for example, like MVTech or NIMAX. And second most voted choice here is by using your own software. And then third, by not using any pre-processing software for my application. And number 4 is done on frame-level FPGA. And lastly, it's done on GPU, such as using NVIDIA graphic cards. Okay, so over to you, Pierre.
So thank you very much for taking part in the poll. So when we are talking about image processing, there are different architectures enabling this. So the most known and used one is, of course, the CPU. We see more and more people using the GPU, while there's also a different architecture that can be used for performing image processing, or at least image pre-processing tasks, and that's an FPGA. An FPGA is pretty different. So while we are looking into the CPUs, there everything is happening sequential maybe slightly in parallel. For the GPUs, you have a much higher parallelism you can use and very efficient and performant processing details, while the FPGA approach is pretty different because there we can use a lot of other kinds of parallelism in order to speed systems up. So when we look into the different approaches, the CPU can do a single instruction on a single data block or maybe multiple data blocks. When you look into some optimizations for the GPU, we can have multiple data, but still single instruction, but we can parallelize a lot. So it's a pretty performant approach doing so. The FPGA is completely different. It can do multiple instructions on multiple data. It means you have, when we look into machine vision, the option to perform a lot of operations or instructions at the same time on multiple data blocks. And in the FPGA, you normally build up a pipeline where all the pixel information, all the lines, all the images and image sequences go through. And since it's programmable hardware, so an FPGA is a field programmable gate array, so you can program these devices and make hardware doing the processing. So you directly program the hardware that something is happening. So when we look in the details, we can do as Basler, we have a very strong focus on the image acquisition, the image transmission, so the transfer into the processing devices. Then we can do the image pre-processing and then later on the further image processing and also image analysis. We can also do tailor-made products, and in order to design these kind of systems or solutions, we have a lot of consultancy services available on our side. So when we look into this, my focus will be looking into the image processing happening on the frame grabber. On the frame grabber, on all of our frame grabbers, we have FPGAs in order to handle the data stream going through. And when we look into interfaces like Camera Link or Co-Express, in each case, you require a frame grabber, including an FPGA. So why not using these FPGAs for performing pre-processing tasks? When we look into GigE or USB, there are normally no frame grabbers are used, but we can use our frame grabbers or the FPGAs on this as a co-processor when you are working with Geeky Vision or USB 2. So when we look into the normal data stream, the data is coming from a camera through a frame grabber, and the frame grabber, by using a DMA, they transfer the memory of the image data received into the host memory, and then CPU and maybe GPU processing take over in order to extract from the images the information the application is asking for. Since the cameras or the sensors and the interfaces are becoming faster and faster, the amount of data coming into a system is increasing, and software still needs to tackle this. But when systems become faster and faster, image processing within the CPU or the GPU needs some support in order to reach the maximum performance levels. So especially with Co-Express 12 coming into the market, the bandwidth is dominantly increasing, and the computational task is causing more and more CPU load due to the bandwidth. So now we are going into the second poll.
Yeah. Okay, so going to the second poll. So the question here is, what are your application challenges that you face in your application? So the poll will open soon. You're given around 30 seconds to review the answer choices and select one or multiple choices. Okay. Yeah, so yeah, thank you everyone for your participation on the poll. So going through the poll results here, you see highest rated poll result choice here is I need to improve inspection precision with better image resolution. And secondly, is I need to analyze big amount of image data quickly. And thirdly, we have choice that I need to control multiple devices in real time. And lastly is regarding other challenges. Okay, so over to you, Bill.
So thank you very much for your answers. So when we now look into the common challenges, it's about high frame rates and very high resolutions. So the data volume in time, so the bandwidth with Core Express 12 can go up to 4.7 gigabytes per second, or when you use multiple cameras in parallel, it can get even higher, and that will definitely become a problem when you work only with CPU and GPU processing. So how to tackle this now? I already explained some details on the differences in between of CPUs, GPUs, and FPGAs, and now for performance, I already mentioned the FPGA several times. So why is the FPGA so powerful? Because when you look at our frame givers, they are really streamlined and they have more or less a passive cooling on some of the devices, and others have only a, they don't look directly as a performance system, but they are. And I would like to explain why they are. So in an FPGA, in these field programmable gate arrays, you can put in your first processing step, second processing step, and so on. So each operation that needs to be performed on the image data flowing through the frame grabber, so from the, for example, Core Express interface through the FPGA, and then the results are directly transferred into the host memory. You can also allocate your user memory and tell the frame grabber, please put the image data, also the pre-processed image data and the pre-processing results into this host memory. This is causing no CPU load so far. So while on the left, we can see that one operation is performed after the other on the image stream going through these devices. And for example, N would be 400 and the FPGA system clock would, for example, be at 100 megahertz. Our frame grabber, it's even higher, but also with 100 megahertz, the calculation shows you can multiply by the operations you're performing on the image data. So we would end up with 40 giga operations per second concerning image processing. So there's a multiplication because all of these operations can work in parallel. So in a spatial parallelism and also a temporal parallelism, let's say, within the pipeline structure concerning the processing. On the CPU, you can also perform exactly the same processing steps, but there one instruction after the other is getting performed on the data going through. So when we here look at 4 giga operations per second, for example, with a system that is having a CPU with 4 gigahertz system clock, we can see that the more complex the processing becomes, the longer it takes. On the FPGA, the bandwidth of the camera and the pipeline within the FPGA will always make sure that you can process all the data coming into your preprocessing device, or the frame grabber that can be utilized. It's simply performing all the tasks exactly at the same time, and the limit is the size of the FPGA, because the programmed hardware is limited in its amount of hardware resources. On the CPU, you just see the more complex it becomes, the lower the bandwidth is. So when we go now into further details on this, especially since it are frame grabbers, the FPGA is representing the preprocessing capabilities within the frame grabber. The image sensor, so the cameras, are connected by the interface. The frame grabber is also having some digital I/O, and FPGAs by nature always act in real time, so in hard real time. So especially real-time tasks, when it's coming into trigger modes, that's the first steps, but also when it's about synchronizing multiple cameras, or even synchronizing multiple frame grabbers and cameras in a single system, or even over multiple systems, you have the real-time capabilities of the FPGA available. And then we have this DMA forwarding everything to the PC and the CPU or the GPU included into this. The DMA does not cause any CPU load or GPU load. It's completely handled by the FPGA itself, so by hardware. So all of these DMA transfers will happen. And before the DMA transfer, or during the DMA transfer, you will have the FPGA working on the data. So during the acquisition, we can also perform pre-processing tasks, and the results are given to the CPU, and the CPU until then has not seen any work. So the load is drastically, so the CPU load is drastically reduced in this time. I don't want to tell you use for everything an FPGA, because that's not true. The FPGA together with the CPU, and optionally together even with a GPU, this is representing a team. And this team in between of the FPGA, the CPU and the GPU, it needs to perform this processing. So I will now go a little bit into the background of when does something get processed. So the acquisition block we see over here, it's the same for FPGA and CPU processing, because the acquisition, it's about the exposure time, the transfer, as you can see here. And after the transfer and the CPU, after the image is received by your application, you can start the processing. Mostly it's, for example, transferred into a Windows operating system, and there we have definitely no real-time capabilities anymore. And the processing can only start after the data transfer. When you use a frame grabber with an FPGA, you can already start looking into the data during the data transfer. So while pixel by pixel, line by line, and image by image is getting transferred through the FPGA can already work on this. So when we see here already the FPGA, when it's a task where no CPU is required, can directly make a digital result output and, for example, control some actuators. Later on, I will show a use case example on this very demanding real-time part. While, of course, things that don't need to be real-time, they can happen in the normal CPU environment too. So you can combine these strings. I don't want to tell you use only an FPGA, but I would strongly recommend use a pre-processing device, like for example the FPGA in the frame grabber, in order to unload the CPU, or make some timing improvements or increase the system throughput in this case. So when a real-time operation that needs to make a digital result output needs to be performed in a CPU, this is normally longer, even when you use a GPU, because it's having the same structure. It needs to wait for the transfer first, and then it can get starting or can start the processing itself. And then we will have some non-real-time feedback on this. But later on, when I go through the use cases, I think this is something you can directly understand then again. So we have this very low latency with a very precise timing, and you can reduce the CPU load. When I'm talking about pre-processing, the pre-processing can also have a very strong focus on making the image acquisition very, very reliable. And since the frame gathers have, for example, the InnoFlex series I will show later on, is having a system clock of 312.5 megahertz. This is representing a timing granularity of 3.2 nanoseconds. So when you want to very precisely trigger a lot of cameras, synchronize these or similar tasks, the FPGA, so the pre-processing device, can also take care of that part. So when I talk about FPGA programming, I will later on mention visual applets, but first of all, we will go into poll number 3 now. So Joshua, can you take over for the poll?
Yeah, okay, so we are into our final poll. So the question here is, are you using a customization solution now? Okay, so the final poll is now open. So again, you're given 30 seconds to review and select your answer. Thank you, thank you everyone again for the participation. So yeah, again, are you using customization solution currently with your application? So the poll results here is 50-50. So half of the participants voted yes and half voted no. So thank you very much for your participation. Okay, so over to you.
Okay, thank you, Joshua, and thank you for your answers. So when we now look into FPGA development, since 2006, we have a development environment. Maybe you heard already about it. It is Visual Applets. So since a long time, we were in the market with a graphical programming approach for programming FPGAs. We don't exclude by this normal approaches like using VHDL and Verilog. So when you are already familiar with an FPGA programming, you will see that Visual Applets is also supporting this. But when it's about machine vision, mostly you have machine vision or application engineers without FPGA know-how, and FPGA programming is in general known as very complex, complicated, and especially it takes a very long time when you want to implement something. This is solved by Visual Applets. So we also internally, for our customers, we use Visual Applets to do customizations. It's having a full graphical interface. It's pretty easy to use. We have a lot of operators in this. You can, during the design time, without having access to the hardware, already simulate on the basis of image data what will happen in detail in the FPGA. So we simulate bit by bit exactly, but still performant, what will happen inside of the frame grabber. So all the pre-processing tasks you would like to shift into the frame grabber, they can get simulated, and then by a very simple build step, so we mostly name it the one-click synthesis, you can make it an applet you can run on your frame grabbers. So these applets, this is the application of the pre-processing step running on the frame grabber itself. So we have a graphical approach that will, without FPGA know-how, enable your machine vision engineers to put pre-processing tasks into the frame grabber. But also we offer this as a service. So when you have a requirement where you say maybe if FPGA is useful, we have field application engineers everywhere in the market who can help you in identifying if your ideas are possible or not, and then we can show you how to implement it, and especially then later on run these applets on the corresponding hardware. So the normal design flow would be doing a graphical design process, designing and verifying exactly your algorithm as you require. Then we have a build process, but this is just a single click, and then you already have your application. So you can attach the pre-processing very easily by using an SDK to your application. So how does such a system look like? So you have the camera, the data is going into a frame grabber, into this FPGA. This will perform the pre-processing tasks on the fly, and then the data will later on end up in the host memory. So the applet running in here is completely independent of the CPU or the GPU processing you're doing, but your host memory will act as an interface. So we will shift all the data by DMA transfers into the host memory, and then CPU and GPU processing can take over. So for example, when you use OpenCV or Helicon, you can directly, or our vTools, you can directly run this on the results immediately. This will work for Linux environments and also Windows environment, the current ones, of course. So when we now look at our frame grabber portfolio, we can see that we have two rows. The lower row here is just about image acquisition. The upper row is about pre-processing or processing devices where you can program the FPGA in there. So we have different interfaces being supported. So from camera link over CoreExpress 6 up to CoreExpress 12. The DMA transfer, so the amount of data you can transfer into the host system. For example, for the ImaFlex, it can go up to 7.2 gigabytes per second from a single or 4 CoreExpress image sources so far. Of course, we bundle this with our cameras, but we also support third-party cameras, of course, when they, for example, use one of the supported interfaces like CoreExpress or Camera Link in general. There are no additional runtime licenses or similar required. It's just a programmable frame grabber you can utilize. They can, or they represent exactly all the functions of a normal frame grabber already, but you can add pre-processing steps to this to have a continuous transition from only CPU processing and then step by step moving more and more options and operations into the hardware. So what operations can you shift into this hardware? So we have a lot of operations available we can use to customize your pre-processing requirements into our frame grabbers. So there are a lot of operators. I don't want to show you all of these 200 operators. I would like to show you what we can do with these operators when we put them correctly together. So as you can see here, we have a lot of different pre-processing tasks. This is just an extract of the tasks we could enable over the last, not 20 years, but it's already more than 15 years. We are doing applications in the market especially on moving pre-processing tasks into the frame grabber in order to speed up systems a lot. So it can be something like HDR, for example. We can do a blob analysis, you can do color space transitions and so on. So now I would like to go into the use cases, because I guess this is the most interesting part. So one very simple to understand pre-processing task is a flat field correction. So to make it more simple, applying a specific offset and a gain for each single pixel we receive in the frame grabber. You can also modify the bit depth by doing this, but the flat field correction in combination with a shading correction will look like this. So it's very easy to understand how it's happening. So everybody who is familiar with machine vision can directly simulate and see how it's looking like. What's the benefit? You can do a very custom flat field correction and shading correction in your frame grabber. And then you don't get inhomogeneous images, you can get very homogeneous images. So what's seen in the background over here is a shading correction that is applied to an image by using an offset and a gain. This is one benefit, but it's very simple, and this is a starting level, let's say. So something more complicated is material sorting. For example, in the glass industry or food industry or recycling industry, or also in other industries, they would like to sort something. So when you have a stream of material, like small glass particles or French fries that need to get sorted if they are correct or not during the processing, this is coming at a constant speed. When these objects come along a line scan camera, then we have a constant time in between of the line scan camera and the jet nozzle. So some image pressure valves that can get switched. Here's just a single one. In real applications, there are more. So while the material is coming along the line scan camera, the data is transferred in the frame grabber. The frame grabber FPGA is performing an object detection on this, and it can already distinguish if it's a good object or a bad object, and then we can switch the nozzle on for the bad objects, and so the dark blue ones, they go in bin number 1, while the good objects go into bin number 2. This is pretty demanding, so I would like to show you how this is looking in reality. So here we have a light. In between of these two lights, the line scan camera is looking through. It can see the dark and white objects. They are just demonstration objects because we don't want to show and cannot show the real application behind. But there are 64 actuators next to each other. And these get switched in hard real time with a very low latency, so that the white objects, they straight fall down, and the black objects, they are shifted to the right by applying a air pressure impulse on these. So they move to the right. So by this you can do very fast sorting while material is falling at a constant speed along the actuators, and they get scanned by a line scan camera in this case. We're really happy that MS Division allowed us, it's a company where we work together a lot on pre-processing tasks, that they allowed us to show how such a system is looking like. Now I go into another case. It's about laser welding. So these two materials need to get welded together. The area scan camera, while it's running at very low resolution, but at a very high frame rate, it requires a very fast pre-processing tasks. So here on the right, you can see a real world image where we measure the melting bath, and then by the size of the melting bath and how it's looking like, it's decided if the laser being used is applying more or less power. So there's a closed loop control that is taking care of a correct welding process. The processing cycle of 60 microseconds, not milliseconds, it's only 60 microseconds, includes the exposure time, the transfer time, the decision-making time, and sending the result into the laser. So with each single laser pulse, the size of the melting bath is measured and directly controls by concerning its results how much power is given into the material. Because when it's too much power, we don't weld, we just make holes in the material. When we don't put enough energy into the system, we don't weld. So the closed loop control is taking care of this part. If you want to solve it in a different way, by, for example, only software, then it's really complicated to keep this processing cycle time of 60 microseconds. So in this case, it's very useful going through a frame grabber where you can freely program it together with us, or we can do this as a service for you, or we can also explain how you can go on with modifications and changes. So you can also protect your IP by this approach. Now I go into print inspection. At print inspection, it's always about the speed of getting the data in and getting it processed. And for example, a color space conversion is a very useful pre-processing step in this case. So the normal white balancing features and so on, they are represented by the color line scan camera. But when it's about complex color space conversions, for example, going into the LAB color space or similar and already doing some pre-processing tasks or finding some markers or other tasks within the print inspection, you can use these kind of approaches. Also, a rotary encoder can get connected to the frame grabber, and the frame grabber is very precisely controlling the line scan speed. So the line triggers are handled very precisely by the FPGA so far. This is now about structured light. It's a little bit more complicated. It's a mechanism where you have a kind of projector that is showing a gray coat or projecting a gray coat on top of your material. So here below you see a real world application with a very white image, then a black image. This is for getting a local adaptive thresholding that is making the system very robust. And then it's going through a pattern that is increasing its frequency from step to step. It's very similar to a binary code so far. So the frame grabber is taking care of the synchronization in between of the camera and the projector in order to generate these sequences as fast as possible. And then the pre-processing also takes place in the FPGA. So what is the pre-processing doing? The pre-processing is using a reliable local adaptive thresholding approach. This is done for each projected pattern for the real data. You can see this 3D printed shark here in the background. This is done for each of these patterns. Then these patterns are overlaid to each other, and then you can make out of the sequence a disparity image. And if you want to, on the left, you can see the gray code, on the right, a binary representation, and based on the disparity, we can represent the height. So it's a single camera system with an active light that can get controlled, and by this you can get 3D data. You can see there's always still a geometric not issue in there, but it's geometrically not corrected. But this is also a task you could, for example, perform inside of a frame grabber. Of course, other patterns are also possible, like phase shifted sinus patterns or the Brownian patterns or whatever. But this is causing a massive CPU load reduction because the acquired sequence is getting pre-processed, and you can, for example, already forward the disparity image into your software for doing the further processing. So you can unload your CPU and GPU system. So the last example for you is about battery inspection. The intention is maximizing the system's throughput by increasing the precision and also the efficiency in this. So what is happening? The system is looking at the coating process over here. And this coating process is causing a very gray material in here. And this gray material should be gray. Everything that's not gray in this coating inspection, everything that's not gray is a potential defect. So now imagine you have a system with several line scan cameras looking at, on the left, you can see an extraction of how these defects normally look like. It's taken from a publication because I can't show any customer images, but this publication is okay. So you can see there are a lot of different defects. These defects normally get classified by using AI or classical machine vision libraries. But when you look at the system setup, you can see that we are talking about processing 1 gigabyte or much more of data. And applying an AI approach onto 1 gigabyte per second, it's nearly impossible. So what do? We do an extraction of everything that is not gray. So all the image data is getting forwarded into the host PC. But next to this image data, we send all regions of interest. So the X, Y coordinates and also the width and the height of the detected non-gray areas. And then the software does only need to look into the image regions where there is a potential defect. And by this, the data amount that needs to get inspected by the CPU or GPU approach is much lower. And when it's much lower, the CPU load, you can use, for example, a cheaper CPU or cheaper GPU, and you don't need to put one completely processing system per camera or similar. So the pre-processing task is happening in the frame grabber. When you're using a high-speed interface like CoreExpress, in each case you will have a frame grabber in your system. So why not using this FPGA inside of the frame grabber for performing some pre-processing that is massively unloading your CPU in this case, while you still have available all the image data. It's just image data together with the regions of interest, so that only a fraction of the real bandwidth needs to get inspected by the CPU because the FPGA is performing the corresponding pre-processing step. So this was my last examples. So when we look at the programmable devices like the Micronable 5 Marathon series for Camera Link and CoreExpress 6, we also have since May now available the ImaFlex series with CoreExpress 12, and they can get directly programmed, so you can get your customization into these frame grabbers. And we don't ask for additional runtime fees for this, so it's just a frame grabber, and you can use this frame grabber also for pre-processing. And how do we normally approach such a development? You as a customer talk to our sales. That will open a normal feedback loop in between of our field application engineers and your technicians. Then we look into the technical project details. We normally make a document of this. Then we put all our experience into this in order to get a very good approach on enabling what you're asking for. Then we can do the coding for you. And at the end, we deliver the applet already explained for your frame grabber. So you can just order a frame grabber and the customization you require, and we can do so. So what are the benefits on our side? In this case, we have a very easy to use development environment that is speeding up the processing or the development approach. And this will give you a very short time to market with a very low development costs. And at the same time, you receive a system with maximum performance. So these technical project descriptions are the first step of getting a customization done for the frame grabbers. And this is how such a technical project description is looking like. So I would like to say thank you very much for your attention. I know that it's technically maybe a bit complicated, so please give me your questions and I hope I have answers for you. So thank you very much.
So thank you very much, Bjorn, for your presentation. So I hope everyone here now have a better understanding on our image processing solution. So we'll take the next couple of minutes, maybe around 10 minutes to answer some of your questions before the webinar ends. Okay, so we have some questions from the floor. So, okay, the first question is from, okay, let me just directly read out the question. So we are developing an egg fertility detection system that will categorize eggs into 3 types. So first type is fertile, second is infertile, and third is dead or perished. So if we want to use the CNN method or the HOG method for object detection, and we already have a Basler ACA 640-90GM camera. So is it feasible to use this type of camera? And additionally, what type of frame grabber should we use?
Joshua, can you please repeat the name of the camera or what interface this camera is using?
Okay, so the interface of this camera is GigE, and the model is ACA 640-90GM.
Okay, this is a very good question because we don't have frame grabbers for GigE. Doesn't mean that, or it does mean that we can't use a frame grabber. We can use the frame grabber as a co-processor device. So you can, even when you have a GigE camera, you can put a frame grabber, even a co-express frame grabber, for example, the IMAFlex, into your system. And the DMA transfer, I mentioned like 7.2 gigabytes per second that you can transfer. So you can move all your GigE data through one of our frame grabbers. Then it's not a frame grabber, in general it is, but the use case would be using it as a coprocessor. That's one step. On the other hand, our cameras include FPGAs, and we can also program the FPGAs within our cameras. There we have some capabilities, and I know that one of our series of the A's is doing it for USB and GigE. So we have a camera series that we can also program by, or we can program it for you as a service. So I could acoustically not really understand what kind of pre-processing task you have, but I see the option that we fill in such a technical project description together with you. Then we have a look if we can move it into GigE camera, because it does not need to be an FPGA on the frame grabber. We support nearly all FPGAs, and we can program these, or Visual Applets can directly program these so that we can use the short time to market approach the graphical programming delivers. So this would be my answer concerning what you would like to do in the camera. That's a part of a longer technical discussion, but using GigE is also possible. You could also use a camera that's using or utilizing exactly the same sensor, but just with a co-express interface, and then you can directly use the native co-express part. So these are the options we have, and that's also something we have already done. But we need to go deeper in exactly what you would like to do. Or Joshua, maybe can you please repeat the algorithm part that was mentioned, because it was very hard for me to understand.
Yeah, sure. So do you like to use a CNN method or the HOG method for object detection?
The first one was CNN and the second was HOG, like histogram of oriented gradients.
Yeah, histogram of oriented gradients, and CNN stands for convolutional neural network.
Yes, okay, thank you very much. So one of our examples we deliver together with Visual Applets is already addressing the histogram of oriented gradients. That's something we can do on nearly all platforms. The CNN part is a longer technical discussion. And in general, can say officially we don't have something for CNNs, but in specific cases we can implement CNN pre-processing at least into the FPGAs by using Visual Applets. But this is again something where we should go through the technical project description where we put all the details together, and then we can give you some recommendations or an approach of feasibility. And that's it, because CNN in general, I would like to say CNNs are more for GPUs, but when it's about very high throughput, we can put simplified CNN approaches into FPGAs. But this is a very specific customization, but we can address it. And I would like to see it and discuss this together with the customer directly, what for options we have. So that was my answer to this question. Do we have additional questions?
Yeah, maybe just one more question.
Yes.
Okay. So next question is, how does multi-threading and parallelism work in frame grabber FPGA? So is it one camera, one thread?
Sorry, can you please repeat the question? I could not understand.
Sure. Let me repeat the question. So how does multi-threading and parallelism work in frame grabber FPGA? So is it one camera with one thread?
Okay. Within our frame grabbers, we support multiple processes, so you can do one process per camera. So when you have, for example, 4 pretty independent machines running with each one camera, and you have, for example, these 4 cameras, then you would like to handle each of these cameras independently of each other because it's a different machine. So you can process the results in a single system for 4 machines with 4 parallel processes. If you require something where the processes start talking to each other, so inter-process communication within the FPGA, there we also have options to do so. You can also combine multiple cameras into a single process. Means, let's say we go for a stereo application and you would like to perform the rectification for both images coming synchronously into a system, then we have a single process where we connect 2 cameras into, and then there is a single DMA transfer at the end forwarding all the data. But it's not only a single DMA transfer we can use multiple of this, so that's possible. The parallelism itself, that was also a question. You can use the pipeline structure in the FPGA. All the data is going through. The more data needs to get processed per second, the higher the parallelism becomes. So when we need a throughput of 2 gigabytes per second, we specify all links in design for 2 gigabytes per second, and then we have definitely a throughput of 2 gigabytes per second going through. When we see we want to run the system slower, then we can easily reduce the throughput per link, and then automatically the FPGA hardware consumption, so the hardware representation of what's done, is getting lower. So then more complex pre-processing steps get possible when you use a lower parallelism. When you increase the parallelism to its maximum, there's still enough FPGA resources available for doing processing, but this is the dependency. The higher the parallelism concerning its throughput, the more FPGA resources get used and the more complex the preprocessing becomes, it also ends up with a lot of FPGA resources going into this. But while having a graphical interface, the representation of the preprocessing into the FPGA is very, very efficient. And I've discussed this a lot of times with FPGA engineers especially. And when we later on were showing the FPGA resource usage, we were pretty close to manual implementations by using Verilog or VHDL. So the efficiency is given, while we can also modify the parallelism easily. So these were my answers so far.
Yeah, so thank you very much, Bill. So we're almost at the, I mean, we are at the end of the webinar session, but I hope that we can have one more question to be asked here. So the other question is, the one who would like to understand if we use two cameras, would the FPGA be able to publish disparity data in real time for 120 frames per second? So this was the question.
Can you please repeat the question again?
Yeah, so the question was, we need to understand if we use two cameras, would the FPGA be able to publish disparity data in real time for 120 frames per second?
So when it's about two cameras, it sounds like a stereo system. 120 frames is pretty independent of the image resolution. But let's assume you have an image resolution of...
Yeah, so it looks like it's two cameras that can output 120 frames per second each.
So with two cameras and 120 frames per second, we can easily acquire this, forward this, and also process this part. If you want to have a disparity image in between of two images itself, it normally requires rectification, feature extraction. And then you can, for example, run the cross correlation after the feature extraction in the CPU. Let's say 80% of the CPU load comes from the feature extraction on stereo. Or if it's about structured light, when it's not stereo, structured light together with the camera at 120 frames per second is possible. It depends, of course, on how you would like to extract the features, how precise, how you would like to cross-correlate those. If you accept it inside of the software, or if we also need to move this into the camera. So this is my general answer on this. Here again, I would really appreciate if we could go through the technical project description approach, where a field application engineer from our side is collecting all the details, and then we can directly give you a pretty good answer on the feasibility. But 120 frames per second, that's something where I clearly say yes. I don't know exactly how your algorithm is working, you are asking for in this case. So here again, we go through the TPD to get all of these details together, because here within the webinar, I guess we don't have the time to go through all of these questions of the normal project approach.
Okay, yeah, thank you very much, Bjorn. And also thank you, everyone. I hope you enjoyed this session with us. Unfortunately, our webinar today is nearing the end. So for your convenience, this webinar has been recorded for on-demand viewing. So, and there will also be a survey at the end of the session. Do remember to fill it up, as it will help us improve future webinars. So again, thank you everyone for joining today. Stay tuned and see you next time.